All right, how you doing, class? This is Properties of Logs, section 12.3. Things get bizarre here, but not if you consider remembering that the exponential and logarithmic functions are inverses of one another. Let me refresh your memory about rules for exponents. Remember when you're multiplying exponents together, you simply, or multiplying powers together, you add the exponents, right? A to the m times a to the n is a to the m plus n. To multiply means to add. To divide means to subtract. And to raise to a power means you multiply. Now, if you just hear those without seeing what I just did, it sounds weird. What to multiply means to add? Well, when it comes to the exponents, that is correct. To multiply powers, you add the exponent. Well, let's look at that from the inverse perspective. To add two logs is to multiply what you're logging. To subtract two logs is to divide what you're logging. To raise something to an exponent means you multiply the log. These things are all true because they are inverses of the other. To multiply means to add. The inverse of that is to add means to multiply. To divide means to subtract. The inverse of that is to subtract means to divide. To raise to an exponent means you multiply. Well, in that case, it almost seems to be the same. To raise to an exponent means to multiply. But this whole idea of bringing this, I can almost draw a picture. And it looks like this comes down front, which is kind of a neat thing. Let me do a couple examples. Before I do that, let me address something maybe I should have said in a previous video. This is the log base b. What if you don't see a base? What if all you see is the word log? In that case, what that refers to is called the common log, and the base is 10. Now, why in the world is the common base 10? 10 fingers. Our whole metric system is based on powers of 10. Our whole numbering system is based on the power of 10. So that's why the common log is base 10. We've not gotten to the base e yet. Or the natural log. We'll see that. I think that's in section 4, if I remember correctly. But let me do a couple of quick examples of how these work. Here's our first example. Let's say I want to combine together 2 common log a plus 3 common log b minus 4 common log c. Now, how can I combine those all together into a single log? Well, what I could do is actually use this exponent property first and take this 2 and make it go up to become an exponent. This 2 log a is the same as log a squared plus log b cubed minus log c to the 4th. Now I have plain logs. Do you notice that a couple of these logs are positive and one of them is negative? The negative ones are the ones that divide, the positive ones multiply. So this becomes a single log. The a squared is a positive log, it's in a numerator. The b cubed is in a positive log, it's in the numerator as well, multiplying. And the c to the 4th is in a negative log, it's divided. And that is the single log from the combination of many. Let's do the reverse of that. Let's say that I've got log of square root of x times y to the 4th divided by 100. All right, so how does this work? Well, you can see that I've got a fraction, just like I had there. Let's see if we can break this into 1, 2, 3 separate logs. So this is log square root x plus log y to the 4th minus log 100. What is the exponent on a square root? Isn't that the same as x to the 1/2? So I bring that 1/2 down as 1/2 log x plus 4 times log y. Now we get to this log 100. Isn't this log right down here a 10? If the log equals the exponent, the base of 10, 10 raised to what number gives you 100? That would be 2. Log of 100 is the same as log 10 squared, base 10. That ends up becoming 2. So we have minus 2. Not 2 log, just plain 2. You can type that in the calculator and prove that yourself. Suffice it to say that when you have a base of 10, however many zeros you have here, that's what the log equals. So this becomes our final answer. Single log separated, multiple logs combined.